What I want to do is entertain you. We'll see if I can do that. I wanted to talk about something that related to MAVEN, but wasn't MAVEN, because you guys are going to get a day and a half of that. And I don't want to overwhelm you the first evening. What I thought I would do is talk a little bit about life on Mars, and in particular I want to talk about the history of the search for life on Mars, because that's something that doesn't often get talked about. People talk about whether there could be life on Mars, but not so much about how we got here. And what I'd like to do is start from the perspective that understanding whether there's life on Mars is very deeply ingrained in our culture. You know, you can see that from David Bowie. I have no idea who those guys are on the left, but it's a TV show that was in England and was recreated in the US. And of course, Marvin Martian. Everybody knows about life on Mars. So what I'd like to do is go over the last 120, 130 years and talk about lessons learned. And as I look around, I realize that there are people in this room that know a lot more than I do about some of these topics. So to you guys in particular, if I say anything that is at all incorrect or misleading, please feel free to just keep it to yourself. Let's go to the next chart. I want to start back with Percival Lowell and canals. We have to start there. Canals on Mars, the Earth-based telescopic photo. Can you guys hear me? Is this okay? Because I can't hear myself. Sounds good. And back in the late 1800s, of course, everybody knew that there was life on Mars. We discovered, when we started looking seriously in the late 1800s, mid to late 1800s with telescopes, we discovered that Mars had seasons, very much like the Earth. That it had an atmosphere. We saw polar caps, clouds. Everything was very similar to the Earth, and people couldn't imagine that there wasn't life on Mars, that there wasn't intelligent life on Mars. And in fact, one of the really interesting things, you go back, you can find front page articles from the early 1900s, like 1906 or 7, quoting Marconi, the guy who invented radio, as having discovered radio signals coming from Mars. And it turns out they were actually coming from the West Coast, but I guess from the spectrum of the East Coast, same difference. It was unheard of to imagine that, of course, there wouldn't be life on Mars. Of course, these weren't real canals taking water to a dying civilization because it's a desert floor. Let's go to the next slide. That era, to my mind, ended in the 40s and 50s. And in the 40s, what happened was we had the first quantitative analysis of Mars, Earth-based telescopic spectroscopic measurements that detected carbon dioxide in the Martian atmosphere. And in the 50s, the first modern attempt to estimate the atmospheric pressure. They got it wrong. They were 10 times too high for reasons that we understand, but it was also 10 times lower than the Earth's atmospheric pressure. So we were beginning to see a world that wasn't quite Earth-like. And when we sent the first couple of flybys, this is a Mariner 6 image on the left, what we saw was a very heavily cratered surface. And although I could sit here and talk about the geology of this and the evidence for water, at the time people saw craters. It's more lunar-like than anything else. And to a lot of people, that was the death knell for possible life on Mars. That didn't stop anybody from trying. And this Mariner 9 image really began to show something different. We saw a very different planet with Mariner 9 than we did with Mariner 6 and 7. And I picked this image because it's got these valley networks, things that actually look like channels, not canals, but channels. And that looked like they were carved by liquid water. Why did they think they were carved by liquid water? Well, it's I think, a very technical, scientific, geological argument. with a flourish of music to you know, the reason we think these were carved by water comes down to the following. They look like they were carved by water. Rob, did that go too fast for you? Do you want me to?
Yeah, could you repeat that? Yeah.
This wasn't the only water carved features. We saw a world. Baird and I mapped Mars, and we saw a world that had abundant water features, that had volcanic features, and volcanoes release water to the atmosphere. It was all of a sudden a geological world, but it wasn't a world consistent with life as we know it. The atmospheric pressure by now we knew was only 6 millibars. 6 millibars? This was, Baird and I was 71, 72. In 1963, we had the first Earth-based telescopic measurements of water in the Martian atmosphere, and it wasn't very much. We measure it in precipitable micrometers. That's how much water, how thick a layer you have if you condensed all the water in the atmosphere. On Earth, we measure it in precipitable centimeters, like 15. So it's orders of magnitude less water. The atmosphere is too thin, too dry, too cold to allow liquid water. So if there was any life, if there is any life at the surface, it has to be very different from what we would expect based on our understanding of the Earth. Again, that didn't stop anybody. We were on a path where there was interest in searching for life. Let's go to the next chart. And we sent the Viking spacecraft. We didn't send Carl Sagan. We sent the Viking spacecraft. That's Carl, and the Viking lander is shown there so you know how tall Carl is. The goal of the Viking mission was to see if there was life on the Martian surface. And they had 3 experiments that were designed to detect life. And they did it by looking for metabolism. They added water, see what happened. Add nutrients, see what happened. And what I think is important, now we're getting into the real science of life on Mars, because we don't know how to search for life. And the reason we know we don't know how is because of Viking and what I'll talk about in a minute, the Allen Hills meteorite. With Viking, what I think is really cool is we had 3 experiments designed to look for life. Every one of them tested positive when they ran it. And each one met the pre-launch criteria that had been written down of what they would see if there was life. I put one of them here. This was the so-called labeled release experiment that Gil Levin did. And what they did was they added water and nutrients and looked for gas that was coming off it. If you add water and there's life, it takes in the nutrients, gives off CO2. So you can see the amount of CO2 going up. That's exactly what they said they would see if there was life. So why don't we think that they discovered life? The reason is simple, although it's going to take me a few steps to get there. First, even though each experiment met the criteria for life, they ran them again as controls. For example, they heated it up to a temperature that would have killed off Earth life. And then they ran the experiment again. They got the exact same result. That really suggested it wasn't life. But the kicker was there was another experiment, a mass spectrometer designed in part to look for organic molecules in the soil. And when they did that, they detected none. They detected benzene and I forget what else, but stuff that was the solvents that they used to clean the instrument. So they knew it was working. But they didn't detect any complex organics. Now you can argue, in fact, Gil Levin still argues, that the sensitivity level of that experiment was too low. But you can't put together a consistent scenario where life is the explanation. And you can put together a consistent scenario where geochemical reactions, water interacting with the soil, with oxidants in the soil, is the explanation. So I think the conclusion I mean, the scientific conclusion is everybody but one person thinks there was no life detected in the sample. Gil Levin still thinks that there was. He's a smart guy. I've talked with him, and you have to take him seriously, but I think he's wrong in this case. The other lesson is, there are going to be 3 lessons here. The second one is, we are not smart enough to predict ahead of time what you're going to see with an experiment as complex as this. Nobody thought there would be oxidants in the soil. Nobody knew what the soil composition was, and therefore nobody could have predicted that you would get results like this just from geochemical reactions. So the second lesson is we're just not smart enough to do this. The third lesson, I think, is the most interesting one, and that is, at the time of Viking, mid to late 70s, people were just beginning to discover on Earth life that lived in extreme environments. Life in hot springs at Yellowstone. You've seen the colors. I don't have a chart here, but you've seen the colors in the hot springs. Those are all organisms that live at temperatures at and above the boiling temperature. Life that lives in plumes of hot water at the bottom of the ocean coming out of hydrothermal vents. And the most amazing one to me, life that can live in nuclear reactors, despite the radiation which everyone says should kill life, because it's developed ways to correct the mistakes that occur when the radiation breaks it apart. It's a self-repairing. It didn't evolve in order to live in nuclear reactors. It evolved in order to live in very dry, desiccated environments. But the same correction and repair mechanism that works in dry environments works in nuclear reactors. With regard to these experiments to look for active metabolism, what we didn't know then is that only something like 1 organism in 1,000 on the Earth can be cultured in laboratories. That means 99.9% of the microbes you can't culture. You can't put them in a petri dish, add water, and see what's coming off. The Viking experiments were well-intentioned, were destined to fail. There was no way they could have worked. How could we think that if we can't culture 99.9% of Earth organisms, we're going to take this soup of organic crud to Mars, scoop it up, and do it there? We learned a hell of a lot about Mars, about searching for life, but this was an experiment that had no chance of success. If we were going to do it today, there's no way we would do experiments like this. The thing that amazes me is the audacity of building a lander like this. We had never landed on Mars at that time. The Russians had tried and failed several times. And to think that the first time we're going to build a spacecraft that in today's dollars is $5 billion, give or take. Maybe it's 4, I don't know the exact conversion. It was 2 at the time. That we're going to build a spacecraft that had life detection capability and land it there. I think a more reasoned approach would have been to put down a lander to do some basic geochemistry and geology. Take a picture, analyze the soil, see what you got, and then figure out how to look for life. We learned a hell of a lot, and we learned a lot about searching for life. Let's go to the next chart. Viking was in the late 70s. It landed in 76, and really the experiments were sort of 76 through 80. The next biggest event in the search for life was the Allen Hills meteorite. And I presume you guys know about meteorites from Mars. I'd be surprised if you didn't, but I'll bring one in tomorrow if you haven't seen one. It's worth looking at. I didn't want to bring it here because I thought I would lose it. And at $1,000 a gram today, I didn't want to lose it. That's out of my own pocket. The Allen Hills, it's ALH 84001. It was collected in the Allen Hills region of Antarctica, where you go out on the ice and most of the rocks to get onto the ice that fall from the sky. It was the expedition in 1984. It happened to be the first rock they picked up. And the comma 0 at the end just means this is a picture of the whole thing. This one is one of many dozens now of rocks from Mars. And if you don't know, I can tell you in great detail why we think it's from Mars, but I'm absolutely convinced. This is the only one that is billions of years old. All of the others are 100 million to a billion years old. This one is about 4 billion years old. And that means that it was present on Mars when water was flowing over the surface. Water would have been flowing through the subsurface. Nick is going to talk about this tomorrow, the evidence, so I'm not going to dwell on it. Within the rock, this is a photomicrograph, there are these holes that have been filled up with carbon-bearing minerals, carbonates, things that would have deposited, dissolved in water and precipitated from water into the rock as water was flowing through it. And in 1996, which is why I put 96 up here, Dave McKay and his colleagues at the Johnson Space Center published a paper where they said they saw evidence for features that could only, actually, I want to get this right. They saw evidence, they saw features that could be explained either geologically, geochemically, or biologically. When you have half a dozen features, and they would all require different processes, they thought it was the better explanation that one process explained them all, biology, and they put that forward. What was interesting is, this gets into the question of how you search for life. We didn't know how to interpret rocks like this. Nobody had ever looked at rocks at this scale, where it was a photomicrograph where they saw things that they thought looked like fossil organisms. Nobody had ever interpreted rocks at that scale, and nobody knew what to look for. Nobody had looked at the features that everybody accepted as life, and the features that nobody accepted as life, to see what the difference was. Over the next half dozen years, there were something like 500 papers published on the Allen Hills meteorite and whether there was evidence for life or not. And a consensus developed. First, consensus does not mean unanimity. There are still people in the original McKay group. McKay has passed on, but others from that group are still active. They believe that they're still seeing evidence for life. But a consensus developed to suggest that most of the things they saw were not biological, but were geochemical. One of the more interesting things is a guy named Andrew Steele at Carnegie, now at Carnegie Institution in Washington, made his reputation by taking this rock and showing that there were terrestrial organisms living in it today. That the McKay group they were looking too close up. They didn't take a step back and see these organisms. That really opens up the possibility that everything you're seeing, if it is biological, is terrestrial contamination. But the consensus is that everything we're seeing here can be explained by geochemical processes rather than biological. People talk about sample return from Mars, and I'll come back to that in a little bit, as the way to find out if there's evidence for life. But if we had not gone through the Allen Hills debate, we wouldn't have a clue what to do with samples. Having gone through it, hundreds and hundreds of scientists developed new techniques, spent years looking at this rock and pieces of it, and figured out a little bit about how to interpret it and whether it's saying anything about life. So I've got a couple of lessons from Allen Hills now. The first is, don't believe the first paper on anything, especially about life. Wait for a consensus to develop. The second one, really I should have said first, is don't rely on one technique. The McKay group put forward about 3 or 4 different observations, including things like this layering you can see, the worm-like things, the chemistry, and you really need to look at a lot of different measurements and look for the most consistent conclusion. That was something we came to with Viking. You know, any one measurement you can interpret in terms of life, but you look at it as an ensemble, and the best explanation for all of it added up was non-biological. Here, same thing. Any one measurement could be interpreted as biological, but just because it's possible doesn't mean it's plausible or probable. You have to look at all of the evidence and say what is most consistent. What conclusion is most consistent with all the observations? And in this case, the answer is not life, but geochemical processes. That doesn't mean there isn't life in the sample. It just means it's not the best explanation. And I think science is about the best explanation, not the most far out or the least plausible. The other conclusion coming out of this one is you're not going to answer the question about life by sending a spacecraft to Mars and looking in situ. You can only do 2 or 3 different experiments. In the case of this rock, they had to do hundreds and hundreds of different analyses with different techniques before reaching a consensus. You put it on a spacecraft, you have to commit a decade in advance, and you've got to commit to 3 or 4 things. And you commit to not doing follow-up. You're not going to get an answer by doing that. Let's go to the next chart. So spirit, opportunity, and curiosity are not life detection missions. They're all rovers. The theme of the program was follow the water. And the goal of these missions, especially spirit and opportunity, but also curiosity, is to look for habitable environments. With spirit and opportunity, they were simple rovers. They were looking for environments that had water. That was the key thing that they were looking for. And they found it. It was a little harder to find at the spirit site than at opportunity. My favorite story about opportunity, when it landed, how many of you guys have eaten seafood at Long John Silver's? Okay, the Berkeley guys are willing to own up to it. Very few other people. When they landed, Long John Silver's said, "We will give free shrimp to everybody in the country if NASA discovers evidence of water." And when they announced their first major results, the company said, "Okay, we accept this. Free seafood for everybody." To me, that is the best evidence that it really was convincing evidence for water on the surface. If they're willing to give away free food, that convinces me. The search evolved, and curiosity, this is curiosity, self-portrait, they held up the arm and took a picture, so you can't see the end of the arm because it's what's taking the picture, but you can see everything else. This was more sophisticated, and it's not just looking for water, which was really the goal of spirit and opportunity. It's looking for habitable environments, looking for places where the kind of life that lives in extreme environments could have survived. The kind of life that lives off of chemical reactions. For example, the type of reactions that occur between water and rock when you put them in contact. Those reactions give off energy. Organisms can stick their finger into it, so to speak, tap into that energy and survive. We see them here on the Earth. Curiosity was looking for those sorts of environments, looking for chemicals that could react with water, looking for evidence for water. So it was really follow the water, follow the life, but not detect life, come up with an environment that could have had life. Now you think about life in extreme environments, and the inability of liquid water to exist on the surface. Curiosity wasn't looking for life at the surface. It was looking, still is looking, drilling into a rock, looking for life inside the rock, looking at rocks that previously had been below the surface, where liquid water could have existed, and it's come up to the surface. The lesson here, this is as sophisticated a rover as we can build today. And really, it's not good for detecting life. It's not well designed for that task. And again, I come down to the conclusion that if you want to search for life, you're not going to do it at Mars. You need to bring the rocks back here. And you need to do that so you can do multiple experiments. Not just whatever we happen to put on the one rover, but a lot of different experiments, a lot of follow-on experiments. Experiments with techniques that have not yet been developed. Because that's the way you're going to find out one way or another for sure. You have to identify the places that could have had life, and I think the key criterion there is water. Find the rocks that could retain a remnant, a memory of that life, collect them and bring them back here to animals. And that's the whole basis, and in my mind, the whole justification for Mars sample return with the idea of looking for life. Let's go to the next chart. So Mars 2020, the follow-on to Curiosity, shown here in blueprint form. They didn't want to pretend the design was cast in stone yet, even though it's using spares from NSL. I guess they don't know what color they're going to paint them or something. They don't know what instruments they're going to put on. They are making design changes. This is an incredibly difficult mission for two reasons. Well, for one reason, it has to do two things. It has to be a compelling science mission on its own right, and it has to collect the samples to return to Earth for sample return. One of the requirements up front for this mission was it has to make significant steps forward on the technology side for sample return. And the science definition team that just published their results said what that means is you have to cache the samples, collect them, package them for return. They stopped short of saying that's the cache that will be returned, because there's no other mission beyond this to return them. But everybody believes that that's what the purpose of this is. I'm sorry, I can't speak for everybody. And I'm not going to say things that aren't in the I believe that that's what this mission has to be. It's going to collect the samples, and a future mission, to be approved later, will go and collect them and bring them back to Earth to study. I think that's the only way we're going to answer the questions about whether there ever was life on Mars. Let's go to the next chart. I want to talk a little bit about the concept of a Mars program. Let me step in front of you here. We've got a whole lot of spacecraft operating at Mars. Mars Reconnaissance Orbiter, Mars Odyssey, European Mars Express in orbit today. Opportunity, I think it's still operating. Spirit, it says down here, completed its mission. That means it died. Phoenix completed its mission, it died. Curiosity is still in its primary science mission, so it is very active. Some goofy mission launches in a few months, and in 2016, InSight rover, Trace Gas Orbiter, that's a European-Russian collaboration. In 2018, ExoMars rover. In 2020, the Mars Science rover. This chart, by the way, I did get from Michael Meyer. I asked him to send me the most current version. And you can see the evolution in the thrust, going from habitable environments to seeking the signs of life. By future planning, I read that to mean sample return. Future planning of sample return, because that's how we want to address the questions. What is compelling here is that we've had this tremendous string of successes in the last 15 years I'm careful not to say 20 years because it was actually 20 years ago this week that we lost Mars Observer. And all of this stemmed out of the loss of Mars Observer. But we've had this tremendous success because we built a program, not just a series of one-off missions. We had a program. Back here over on the left, off the chart, was Mars Pathfinder with the Sojourner rover. We needed to do that, to reinvent the capability of landing a package on the surface, to find out how the heck you do a rover mission with this rover this big that went 100 meters or so. Building on that success, we designed Spirit and Opportunity, much more capable rovers that really had compelling science missions. And then after that, Curiosity. Each one built on the one before it, both technically, technologically, and scientifically. But we don't need to shoot this. We can get copies of all of this.
But we want you in front of it.
Dave, you can shoot me. I'll heckle you tomorrow. Come on, Dave, this is my job. I don't come to your job and heckle you. Oh wait, yes I do. We've been able to build on the technical capability and the scientific success in order to get more and more capable missions that can answer harder and harder and more interesting scientific questions. On the orbiters, same thing. Way off on the left here was Mars Global Surveyor, which did some of the recent in my career mapping. Odyssey and MRO built on that. MAVEN builds on that, and NASA used to be going to do a trace gas orbiter. That would have built on it. Now ESA and Russia are, but that builds on the scientific success. We can only do this because we have a program, and we were on the verge of losing that. The program was canceled. The budget cuts did kill it, but we still have the 2020 science rover, which would have been the next one in the program. So I think we still may have a program. We have to wait and see what happens. We have to wait and see whether they can bring that cache of samples back. That's, by the way, C-A-C-H-E, not C-A-S-H. Very important distinction, although they often get confused. Let's go to the next chart. Actually, before you do, I want to point to this one, which is notable in the context of what I'm talking about tonight by the fact that it's not a life detection mission. Now, its goal is to solve Mars climate mystery. That's our new tagline. You can see that popping up. MAVEN is about understanding the history of the Martian climate, understanding where did the water go, where did the CO2 go, and how did it change from an environment where water was present on the surface early on to an environment that's a cold, dry desert planet we see today. To my mind, it really is an astrobiology mission because it's all about understanding the history of the habitability of Mars by microbes. This is the picture we've been using ever since our original proposal. If you forget that, just ask me what time it is because I've got the same picture on my watch. This is supposed to be current Mars, and everyone thinks that's Earth. It's ancient Mars that may have had an ocean and a thick atmosphere. And it's sort of, we really see this one, but we see evidence of ancient Mars with all the water peeking out underneath the surface. This is the next mission. It's going to be the next spectacular mission, of course. No bias at all here. But really, I do see the search for life on Mars as being the overarching theme of the program. It's the goal of the program to answer those questions. And if we don't return that cache of samples, we've walked away from being able to answer those questions. It's possible that we'll detect life on other planets with radio telescopes using SETI, or with optical telescopes now that we can detect planets around other stars. But the best, closest, most likely place we're going to answer the question one way or another, it's going to be at Mars. And we're going to do it, if we do it, if we don't give up on this responsibility, we're going to do it by continuing this program and taking the next step. And if we don't, we're really walking away from a willingness to answer these questions. And to me, what makes this exciting, let me start that sentence over again. To me, it is exciting that we as a society want to answer those questions, that we're interested enough in the world around us writ large to want to know whether there's life on Mars, to want to know whether there's life on planets around other stars. We've discovered all these planets now. What else is out there? We're interested in understanding life because we are life. We want to understand how we relate to our planetary environment. We want to understand how all these other planetary environments we're discovering relate to the possible presence or absence of life elsewhere. I think these are the important questions, and to me, this is what makes it exciting to get up in the morning, to think about exciting questions. These are questions that affect everybody. You know, I remember getting in a cab in Washington, and if you've ever done that, you know that they're generally not driven by PhD scientists. Well, a few from Russia, but not a lot of them. I got into a cab and said, take me to NASA headquarters, and the cabbie starts talking about water on Mars, and the recent discoveries, and the possibility for life. It only deflated me a little bit when the next sentence had to do with visiting by UFOs and alien abductions. Same thing. He's interested in life in the universe. It's something that will affect everybody if we find it. You know, it's not going to affect our day-to-day lives. Well, maybe mine, my funding might go on. Other than that, it's going to be a deep philosophical impact. So I'm really glad to live in a world that is interested in answering these questions. Well, it's interested in asking the questions and has the willingness to try to answer them. And I will stop there. Stephanie, thank you for letting me fill in for Michael when he couldn't make it. It's really a pleasure to be able to talk to you guys about my favorite subjects, and I look forward to the next 1.5 days. Thank you. If anybody has burning questions or wants to argue with me, I would be delighted. Yeah.
I'm kind of a exuberant person or whatever.
You don't look like him.
I know. I'm all for sample return, but I wish we'd just go ahead and send human astronauts and figure this out the easy way.
What I have learned in the last 10 years working MAVEN is how hard it is to send even a simple spacecraft. To give you an example, before we can launch MAVEN, we have to verify every one of 10,000 requirements that were written down, things that this thing has to do in order to succeed. And if we miss some or if we screw it up, that's when we lose spacecraft. The software, I actually learned just yesterday, you have parameters that get stored in software that affect how the thing runs. 27,000 parameters have to be entered into the software to run MAVEN. We don't have the capability today to do sample return. We have to invent new technologies. I find it hard to believe that we can put together a credible case for being able to send people today and successfully return them. I am really excited about sending people to Mars, you in particular, but no names. I look at the chaos in the human program, and I think I'm in this business because I was 6 years old watching the countdown of the first Mercury astronauts, and how exciting. I would hate to think of a world, of living in a world that has no human exploration, that isn't aimed towards sending people to Mars. But it's really hard to do, and I don't see anybody today willing to make that commitment to doing it today and doing it right.
Yeah, I think the way it's going to work is probably there's going to be some half-baked attempts. Like Mars One and all that, but sooner or later it's gonna happen.
I agree, and I'm excited about the possibility, but it's not easy. And when you have people's lives on the line, I'm not willing to accept what a lot of people say of, hey, take me, I'm willing to go even if I don't come back. I don't think that's acceptable to our society.
Well, if they're willing to go, I'm more willing to
Fair enough.
So with regards to sample return, is the lab capability now on Earth good enough to answer the question? I mean, what if we get these rocks back and we're still arguing about it?
Depends on what the rocks have in them. That's a really good question and a really tough one. Given what we know about life on Earth today, I think we could go someplace, pick up a sample, if we choose it carefully, choose the place of the sample carefully, and go back and see if it has, and we would be able to find out if it has evidence for any of the things that we've seen on Earth. That doesn't mean that's what life on Mars would look like. For example, before, people talk about life as we know it, before the DNA-based life on Earth, people believed there was RNA-based life. You don't know what that would look like. How would that be reflected in the fossil record? Don't know. But nobody's found rocks that have that on Earth, or knows how to recognize it. And maybe that's as far as life got on Mars, and maybe we wouldn't recognize it. But I think this is a chance I'm willing to take to say, let's go, let's find out what we get when we bring samples back. If it doesn't have life, or if we're unable to answer that, we still learn a tremendous amount about Mars. And we do know places, we do know where to go to look for that evidence today. In terms of would it answer the question, that's a hard one to answer. A determination of whether there's life, I believe, would be done by consensus. Everybody looks at it and goes, oh my God, it was alive. And you've got a consensus. Or you get into arguments that will take decades to resolve. But I think waiting until, if we aren't willing to do it now, the alternative is to wait until there's a more compelling reason to go do this. And the only thing that could be more compelling is already having detected life on Mars. And I don't think we want to wait and just have sample return as the confirmation. I think we can go and answer the question, but it depends on what Mars throws us, and we're going to learn a hell of a lot. And I know that there are people that doesn't satisfy. To me, it's a compelling argument. Yeah.
So there's, to my knowledge, no high-res imaging capabilities unlike other missions that were before us. This is a question, particularly for this audience, how are you going to engage the public without any kind of visual handy to give them?
You asked me that in a year, and I figured that out. That's a really good question, because one of my fears is that although the scientific arguments behind the search for life are very compelling to me and to many of the people in this room, we've been having this same debate about Allen Hill's Viking sample return for 15 years. How long can we sustain the public interest in that to keep moving down this path? The fact is, it is hard to answer these questions. We learned with Viking, you can't just send a spacecraft and get an answer the next day. We learned that again with Allen Hill. It takes a concerted effort, and it's not one that you can do in a year or 2 years or a decade. I think we've got another decade easily in front of us before we can get an answer. And that's how long it takes to send 2020 and then send something to go collect the samples and bring it back and then do some analysis in the lab here on Earth. And even then you may not have an answer. How long can we sustain the excitement and interest of the Washington, D.C. cab drivers? I don't know the answer to that, but it's a real concern especially when every 6 months you read another press release about the discovery of water on Mars. Yeah.
Let me interrupt and say, Camille, it's not just a question of how will the MAVEN team engage the public. How will you engage the public? And how will all of you that we've invited?
Wait. Be careful, because I don't expect the reporters to have an agenda. I do have an agenda, and that's getting sample return mission, getting science, and getting far enough. To some extent, they're reporting without having that agenda. They lose credibility.
She was asking about MAVEN specifically, and that's where we are.
Yes, I was.
Oh, okay, I'm sorry, I took it as a broader question. Asked me in a year and a half. You know, MAVEN isn't an aeronomy mission. We've never used that word. Aeronomy is the science of the upper atmosphere. I even mentioned it here. It's an astrobiology mission. It's about habitability of planets, habitability of Mars. I think that's the hook, that's the basis we sold it on. And when we come back with our science results, that's what we're going to focus on. Where did the water go? Where did the CO2 go? Why did Mars go from being a habitable planet to one that isn't habitable? And I hate to think that we would have to live in a world where to get on the front page of name your favorite newspaper, we had to invent a reason to put a camera on the spacecraft that wasn't going to contribute to the goals of this mission. We have a compelling science mission, and that's how we're going to present it. If the public isn't interested, they'll wait for Mars 2020 or Curiosity results. Now, how many of you guys know about the results from the WIMP spacecraft or the Polar spacecraft? Those are names of Earth orbiters. And probably not many, but those are missions doing compelling first-rate science that doesn't get on the front page of the newspaper every other week.
Is MAVEN going to address the anomalous methane readings from other missions? Is not equipped to do
No,
that?
we don't have a methane detector, but the trace gas orbiter, the ESO Large, will.
You know, you mentioned Mariner going back in time, and I never, you never get caught up on going back and looking at what the science output from those early missions were like. Were the things in those detectors and those instruments that were flat wrong, that just threw people off in the cockpits, or I mean, how coherent was the data over the decades about Mars?
The examples I know of, the data was coherent.
Yeah.
The scientists weren't.
Okay.
The issues were never with the data. It was always with the interpretation.
Yeah, well, that's what we expect that to be done.
What,
I expect you guys to interpret what you got. Now, why was there such discrepancy? I mean, what was it? I don't even know if I'm right. Is there anything that was really skewed that was totally wrong? That you can think of?
The first example that comes to mind is the detection of organics from the Mariner 9 infrared spectroscopy experiment. Flat out wrong. It was a mistaken interpretation by a scientist who should have known better. There's an example. The press conference, detection of organic molecules, really a big deal. Well, not so much.
Okay.
There's also a question of sampling. I know those first Mariner 6 and 7 images happened to be from a part of the planet that was very boring. It didn't have any channels in it. So for those 2 or 3 years, people thought, oh, this is the moon.
Yeah.
So it was sampling, it was resolution. Even with Mariner 9, there's a lot of detail that we couldn't see. So it's not that the data was wrong, it's just that it wasn't sufficiently portraying what was there.
So we expect no mistakes out of this mission.
Absolutely.
Look at this practice.
Yeah, I know.
You should always expect no mistakes.
Okay.
Shannon?
You mentioned the fact that the Soviet Union crashed into things over time, and they were not very careful about planetary protection standards. Do you think there are in fact infected areas left over from that era? The things that survived to this day, if they're in shadow or buried under hardware?
Yes. And I'm thinking in particular of the Russian landers that got all the way down to the surface and then failed. They had relatively soft landings. I think some of the analysis, what's called breakup and burnup analysis, has shown that if you auger in at full speed, you're going to kill all the organisms. But with a soft lander, maybe not. In fact, even the Viking spacecraft had an estimated 500,000 spores that could be brought back to life in theory on the spacecraft. We have to do planetary protection. That is the benchmark for us. We have to make sure that when we ultimately crash onto the surface, we don't carry with us more than that same 500,000 spore equivalents. Jasper.
Given that issue, do you think that we can curate samples from Mars 2020 or a mission like that well enough to be completely unambiguous if we do find evidence of life?
Yes. We know how to do it. We do it with Ebola virus all the time. It's been decades since anybody in a lab has come into contact with that. We work with things that are, I don't mean me, of course. We work with things that if you come into contact are fatal a significant fraction of the time, and we know how to deal with it and do it effectively. Yeah.
Would we see, with a sample return mission but returning sample of atmosphere, like that skimmer proposal that didn't go forward, would we see anything like the value in that kind of sample return compared to your comparison of what Curiosity is capable of doing compared to bringing some rocks back?
I think you have to ask what are the questions you're trying to answer. If you bring back a sample of atmosphere and atmospheric dust, you're dealing with weathered materials in the dust and the atmosphere, and you're going to be able to answer questions that those materials are suited for. If you want to answer the question about life, I think you have to fall back on what I described. Bring back well-characterized samples from the best places, not a random sample of dust that happens to be in the atmosphere. And in particular, bring back the types of rocks that are capable of retaining fossil remnants from possible life. So you have to tune your samples and your mission to what you're trying to get out of it. Yeah.
You talk a lot about how difficult the problem is for sample return from the surface of Mars, and he's talking about skimming the atmosphere. What about, say, a sample return from Phobos? Would that be, or Deimos? Would that be an easier proposition?
It would be a lot easier. I'm blue about that. I've heard it suggested that if you go to the surface of Phobos or Deimos, you can walk around and pick up Mars rocks off the surface.
Exactly, if you blast them off the surface.
Yeah. But those would be a random assortment of rocks, and you wouldn't know where they came from. We have that already in the Martian meteorites, so I'm less optimistic about the value of doing that than again going to the best place you can identify and bringing back rocks that you know where they came from.
Well, that brings up another topic. Because we haven't really discussed, I guess, or haven't come up with it. There's not going to be, it seems to me, there's not going to be any kind of life that we would recognize like Earth-like life on the surface anyway, because essentially the perchlorates and the UV radiation, all that's going to kill it. So we have to get subsurface samples, don't we, or something like that, or something from an aquifer or something.
What you want, what I think we're looking at, and this is what the science definition team for 2020 came back with, is to not look for extant life living there today, but to look for fossils of life from a previous time. So when you're doing that, you can go to rocks that used to be where the water was. And if you pick a 4 billion year old rock, that could be at the surface, it can be beneath the surface. If you go to a 2 billion year old place, you can look for a rock that used to be beneath the surface. So I think that's a very straightforward problem. I would not be optimistic about finding evidence of life on the surface today unless we went to a place where there was liquid water actively coming out and bringing it from below the surface.
Right. Like on one of these, what do they call them, gullies?
Yeah, a gully. There are also some things that look like surface expression of aquifers that MRO has imaged. There's a number of places, but none that I could point to today and say, that's the gully I would go to.
Well, so somebody tweeted me about something. I said, where would I, somebody was tweeting about where would you like to go on Mars? And I always said, you know, the Mariner Valley would be a good place to go. And then they tweeted something about, oh, there's probably water on the surface down there.
Probably not on the surface, but there used to be. There's a lot of evidence that there had been standing water within Valles Marineris.
Right. I don't know where they got that from. I just saw it on Twitter.
But I'm sorry, in that case, it must be true.
Well, I didn't buy into it so much as I just wondered, what were they going on about? What were they talking about? I never heard of any water on this being discovered in the Mariner Valley, surface water.
How would you unambiguously determine that whatever evidence for life was there was from Mars and not Earth? Or not? What's the unambiguous determination?
That's part of the reason why you need to go and collect the samples rather than looking at Martian meteorites. The Martian meteorites have been heavily processed since they were on the surface of Mars, not least of which is they fall to Earth, and most of them are picked up in the ice in Antarctica, and they pick them up out of puddles. And there's Earth life, identifiable Earth life, that had gotten in there from those puddles. But if you go to Mars, you pick it up, you bring it back, you follow appropriate contamination
That's presuming it wasn't contaminated by anything that we landed there.
But if we're looking at fossils, presumably what's in there is not that
Yeah, that's what I'm asking, yeah.
Someone's been dead for 3 billion years.
Right.
Yeah.
Unless we're their descendants.
That's the tough one. If you find Mars life that is identical to Earth life, does it represent a common origin? Or does it represent an independent origin because there's only one solution to how to create life? Or was it transfer? How was it transferred between planets? Those are cool questions.
That's one of the questions I got on Reddit today was, could life on Earth have come from Mars? And I said, probably not, because we can't.
Why did you say probably not?
I said there's no good evidence for it, but since pieces of Mars do land on Earth, it's not like it couldn't have happened.
But there's no good evidence is different from probably
Sure,
not.
okay, I misspoke. There's no good evidence.
I'm just poking at you for fun. But how you cast these questions is very important. And you have to make sure you're being very careful about how you want to answer them and how you ask them.
Do you have any thoughts on how, if we brought a sample back, would have to be quantitative? Because there's a lot of, you and I want to bring the sample back, but there is some controversy in the general public whether, it's good for reading and drama.
Let's say take it to the ISS.
So what's your thoughts about that? Right.
It's not just the general public that's a real issue.
Right.
If you don't know, you want to err on the side of caution. What was that? You want to err on the side of caution. I would hate to be the one responsible for bringing back something that caused the Andromeda strain, or if you've seen the movie I Am Legend, that's not how that happened, but I would hate to be the one to cause that. You have to be pretty damn sure of being able to successfully contain it.
So would you bring it back to the ISS first? Bring it to Earth?
I think bringing it to the ISS is a problem because suppose you do that and an astronaut gets sick, do you just leave him up there to die?
Oh, better to kill the
Well,
rest
it's better than people on Earth. I mean, that's what some would say.
Yeah.
I'm not saying.
I don't have to make that decision, fortunately.
Because there are some people who have suggested that if you bring a sample back, we even should sterilize it.
If you're just looking for fossils, like this isn't a big deal.
In which case, you know,
These
you're
are
destroying the very evidence.
these are ongoing discussion topics, and there aren't good answers to them.
That's why I'm asking.
Right.
Part of the nominal budget for Mars sample return is I think a $200 or $300 million facility to make damn sure there's nothing in there can get out.
Let me suggest that we stop and not try to answer all the questions tonight. We have a day and a half about an even more exciting mission called MAVEN coming up. And talks that will relate it back to life in sample return.